Welcome, everyone. For today's prep, we're going to start our velocity and acceleration packet here. And what we're going to be doing, well, not in this video, but we're going to be doing in class, is we're going to see how we can use derivatives to help us investigate the physics of motion in a straight line. So we're just kind of motion in a one-dimensional universe. And for today's prep, we're going to look at just the kind of the premise here, motion in a straight line. All right, so the main function we're going to be working with when we talk about velocity and acceleration is called the position function. And let's read through what the position function is going to do, and we'll draw a diagram kind of explaining this. So usually we let our position function be called s of t. And what this does is it tells us where our object, so we're going to have this object that's moving around. This is going to tell us kind of the location, the position, where our object is at time t. And our object is going to be moving along a straight line. So, some classic examples is, you throw a ball up and it goes vertically straight up into the air and then it falls back down. Or like a rocket. Or you could imagine a car driving down just a straight road. So things like this. And our universe that we're going to be looking at is, well, just a straight line. So here's our line that our object's going to be moving on. So let's put our object somewhere. So there it is. There's our object. And you can imagine, maybe it's like a particle that's moving around. So, or like a spring. You can imagine a spring bouncing back and forth in a vertical or horizontal line. So we have this one object, and it's just moving back, and maybe it's moving forth and just bouncing around and traveling along this straight line. All right, so what our position function is going to do is it's going to tell us where this object is at any time. Well, in order to be able for us to say where exactly it is, we need to have a reference point. So on this line, we're going to pick one point, and we're going to give this point a special name. We're going to call it the reference point. So imagine like the x-axis or the y-axis. If we're doing horizontal motion, imagine just the x-axis. If we're doing vertical motion, imagine just the y-axis. The reference point then you can think of as like the origin. A lot of times you can think of it like the origin. And just like with the x-axis and the y-axis, there's kind of two sides relative to this reference point. There's the side over here, and then there's the side over here. So we want to make some directionality here to our universe. So we want to be able to distinguish, is our object on one side or is our object on the other side? So we normally make one of the directions positive, and then we make the other direction negative. Just kind of like our x and y axes. So on this diagram, I'm going to make this side the positive direction, and I'll make this side the negative direction. Kind of like our x-axis. But there might be situations where maybe you want to reverse it. So maybe you're more interested in things over here, so you want to make this the positive direction, and so this would be the minus direction. Certainly plausible. All right. So what our position function does is it tells us how far away our object is from that reference point. So it tells us the distance. And then it also tells us which direction. So it tells us kind of two pieces of information. It tells us how far away, and then also which side of our reference point we're on. All right, so let's look at an example. So a ball is thrown up into the air, and we have this position function s of t, which denotes the height of the ball in feet after t seconds. So our position function here is negative 16t squared plus 128t plus 5. And we want to know a few things. We want to know what is the position of the ball after 2 seconds. And we also want to know when is the ball at a height of 117 feet. So before we get to these questions, let's kind of draw a little diagram for what's going on. So we'll draw it over here. Now, we're throwing a ball up into the air. So this is going to be vertical motion. So let's draw our one-dimensional line. Okay, there we go. And, well, what is our reference point going to be? Well, kind of a natural reference point when we're talking about things being thrown up into the air, kind of what we would expect, the reference point would be the ground. So we're going to make our reference point the ground. All right, so imagine that we're standing, there we are, we're standing on the ground, and we're going to throw our ball straight up into the air. There's no wind or anything, so it's just going to fall back down. So our ball is going to travel along this path. So it's going to go up, slow down, eventually it'll hit a high point, and then it'll start to fall back down. All right. So we also have to decide what do we want to make the positive direction? Well, there's kind of a natural way to do this. The positive direction is up, kind of like our y-axis. And so that means down we're going to make that the negative direction. Okay. So our ball, our little ball here, is going to be traveling along this line. So we've got motion in a straight line. And we have the function that describes, so this function describes where our ball is at any time t. All right, so let's answer the first part of this. We want to know what is the position of the ball after 2 seconds. So our ball, we're throwing it up, and we're going to count to 2, and then we want to know where is our ball? How high up is our ball? So the way we can answer this with the position function, and let me come on back here. The way we can answer this with the position function is we're just going to take our time, which is t equals 2, and we're just going to plug it into the position function. We're going to evaluate. So we're going to evaluate our position, s of t. So we plug 2 in, and wherever I see a t in my formula, I'm just going to swap it out with 2. So we get negative 16 times 2 squared plus 128 times 2 plus 5. All right. And perfectly fine. Numbers are kind of big. Just leave it like this. We could probably simplify this down. We could probably calculate it. If you wanted to use a calculator on something like this, I wouldn't necessarily disagree. But actually the numbers here aren't too bad. So this is negative 64. And this is 256. And then we've got our plus 5. And if we simplify that, we want to do 256 minus the 64. So that's going to be 192. And then add in the 5, and we get 197. All right, so it's, first of all, a couple things here about this number. It's positive. So that tells us, if we kind of look at our diagram again, the fact that it's positive is telling us that relative to the ground, this ball is in the positive direction. So it's somewhere floating up here. So it hasn't drilled down into the into the ground yet. Now, whenever we're dealing with these application type problems, we want to look for units. And in this case, we have the units of our function are in feet. And then we also have our units of our variable, which are seconds. So because we evaluated our position function, the units for this value here are going to be the units of our position function. So it's just going to be feet. So the position function is telling us our ball is 197 feet up in the air. So this is just one of the games we can play with a position function. We want to know where our object is at a certain time, just evaluate it. Well, we can kind of go the other way. We can also use this function to make predictions about where our object, when it reaches a certain point. So what time does it reach a certain height? And that's what we're going to do in the next one. We're going to look at when is the ball at a height of 117 feet. So it's like we have the position and we want to work backwards. We want to figure out the time. So in the previous one, we had the time and we were able to just plug in and get the position. Well, now we have the position and it's like we want to go back. So this is going to be a little more difficult. So the idea here is we're going to take our position function and we're going to set the position function s of t equal to 117. So that's the height that we're interested in. And then once we do that, we're going to solve for t. All right, so let's see what we get. So we make let's set our function. So we'll get negative 16t squared plus 128t plus 5. So just our regular position function there. And we're going to set it equal to 117. All right. So we want to solve this equation for t. So the way to do this is, well, try and get all the terms over to one side. So I could subtract 117 from both sides. Maybe that's the easier way. I don't like this negative, though, in front of the t squared. So I'm going to actually move all of this stuff over here with the 117 so that I can make this one positive. Just makes the solving a little bit easier sometimes. So if we move the terms around, this is going to give us the equation 16t squared minus 128t and plus 112. All right, so we have this equation to solve. And there's a few ways we might go about this. One, it's a quadratic function, quadratic formula, so we could use the quadratic equation. Perfectly good to do that. Another thing is maybe this factors. So I recommend try factoring. It's a little bit easier normally. And if you can't factor it, then go to the quadratic equation. So first of all, we have this 16 in front of the t squared. So we want to factor that out. And we want to think, is 16 a factor of 128? So does it divide nicely into it? And does it divide nicely into this 112? Turns out it does. So 16 is a nice factor here, and 16 is a nice factor here. So start by factoring out the 16. And it factors out of 128 by 8. and then it factors out of the 112 by 7. All right, so once we get this simplified, then we want to keep on factoring. So we can factor this now a little bit easier. The numbers are smaller. It's always good to try to make the numbers smaller. And it turns out this factors nicely into, well, we still got the 16. Factors nicely into t minus 1 times t minus 7. And again, you can check with your factoring. So if we take the negative 1 and the negative 7, multiply those together, we get positive 7. That checks. And then if we take the negative 1 and the negative 7 and add them, we get the negative 8. All right, so once we get this factored, then each of these individual factors here is going to give us a solution. So we've got the t minus 1, and then we've got the t minus 7. So this factor will give us the solution t equals 1, and this factor will give us the solution t equals 7. And the 16, that doesn't give us anything. That's just a constant. So this doesn't do anything for us. And if you wanted to, we could divide both sides of this equation by 16 and just get it completely out of there. So only the variable stuff gives us a solution. All right, so what happens is we found the 2 times when this ball reaches a height of 117. Now, what are the units here? Well, the units for time in this case are seconds. So after 1 second, the ball reaches this height, and then again after 7 seconds, the ball reaches this height. And this should seem plausible. So if we go back over to our diagram, let's say this is our 117-foot line here. Well, when we throw the ball up, it's going up, 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 slows down, stops, and then it starts to fall back down. So it's going to cross that threshold twice. Once on the way up, and then once on the way down. So it makes sense that we're getting these 2 different t values. All right, so we're going to see in class, kind of to spoil it a little bit, we're going to see what the velocity function is, do some calculations, and then we'll also see what acceleration is. So we'll see you then. Bye-bye.